Good morning, everyone. Uh, Today, let us continue our discussion on the group 2 elements. And today I'll be discussing with you the last topic in the group 2 elements. So in that last topic that I will be discussing with you, what I'm going to discuss with you is the anomalous properties exhibited by the beryllium compound. So as I told you previously when we were discussing the group 1 element, at that time I told you that the first element of every group behaves in an anomalous manner, that they differ a lot with respect to other elements in the group, as well as they exhibit some kind of diagonal relationship with the diagonal elements of the other group. So all these anomalous properties can include not only the difference that they have with the elements of their own group, but also their diagonal relationship with the element of the other group. So those points for beryllium, I have noted it down. So we will be discussing them. Let us go through them one by one. So one of the properties, one of the first point that we are going to discuss is regarding the melting point. So what do you find here is that what I've written here is the melting point of the fluoride, beryllium fluoride, and compared it with the fluorides of the other elements in that same group too. So what do you see the difference? You see that the beryllium compounds, fluoride compounds, are having a lower melting point compared to the fluorides of other elements because they are exhibiting a range of 1,000, more than 1,000. So why there is a difference in the melting point? The reason why you see a difference in melting point here is because beryllium, being very small in size and therefore is having a higher charge density, and according to Fajan's rule, they exhibit more of a covalency. So beryllium compounds are more covalent in nature rather than ionic compounds. So that is why being covalent makes the melting point a little bit lower in comparison to ionic compounds, because we know that ionic compounds exhibit higher melting points. So that is why you see a lowering of the melting point here in the case of fluorides of the beryllium compound. Talking about the hydride, here again the thing of covalency come into picture. The beryllium hydrides are kind of exhibiting a covalent nature, and therefore in an anomalous manner they also show polymerization, making these structures highly polymeric rather than existing as a simple molecule such as BeH2. So beryllium hydrides are not usually existing as BeH2 in their solid form, because a BeH2 you will usually found in their vapor form, but in the solid form they would be found found to have a polymeric nature. So polymer is formed only by covalent compounds. So that is why I'm saying that beryllium compounds exhibit a covalent nature, and that is inherent because of the small size and high charge density over the beryllium atom. However, we compare the other hydrides, they are all ionic in nature. So in the live session, we are going to discuss about this particular hydride and their structure and how the bonding exists in these compounds. Talking about the beryllium halides, they also exhibit similar nature because both these compounds, they are not existing as a molecule. They are existing as they both are not existing as molecules, not molecules. Okay, but they try to cluster together to form something called cluster compounds. CLUSTER. So this is nothing. I'll write it again. So it is CLUSTER. USTER. So this is called cluster compound. So basically, beryllium, on account of it exhibiting covalency, they form these cluster compounds. Now, cluster compounds are formed whenever there exist when the molecule is not able to complete its octet, or its electron deficient. So in such cases, these molecules try to cluster together or come together to form kind of polymeric uh, bonding, so that such compounds are called cluster compound. Now, why they form these kind of compounds form uh, these polymeric compound is what we are going to discuss in the live session, where I will be talking about the bonding and why these compounds are electron deficient, and that's why there is a need for them to come together to form a polymeric compounds. Okay, so that is why these such compounds, in which they don't exist as a molecule but rather as a cluster of molecule, so such compounds where you find such kind of clustering, they are coming under the category of cluster compounds. Now, though they are both are electron deficient, and therefore they are forming a polymeric nature, and when you see the structure of both these compounds, they are very similar in nature. But when we talk about the bonding present in them, they are completely different in type. So that is what we are going to discuss when we are talking about the structure of halides as well as hydrides of beryllium in the live session. Another important anomalous property that the beryllium compound exhibit is the formation of complexes. Now, for the formation of complexes, a very important characteristic is that they should be smaller in size, and they should have high charge density, as well as they should have vacant orbital. So beryllium exhibit these properties, and therefore beryllium shows complexation, and you will find many complexes of beryllium compound. Now, important thing here you have to note down is that since beryllium is coming under the second period, so it will have only 2s and 2p orbitals. So only 4 coordination number is possible for beryllium compound, not more than 4, because it cannot expand its valency beyond 4. Okay, so apart from beryllium, magnesium and calcium also form complexes that we know about. You find magnesium in chlorophyll, and calcium also you find in certain complexes. So that is why it is some of the elements in the group also exhibit the complexation, but not every element in the group. So beryllium forms more different types of complexes with a coordination number of 4. Another property which we have discussed when we talked about the beryllium hydroxide in the previous class. So here beryllium also shows our amphoteric in nature. Now, why I say beryllium metal or beryllium element as such forms is an amphoteric is because if you remember when we tried to talk about the reactivity of group 1 elements, we found that group 1 elements when they react with acid, they form the corresponding chlorides, and therefore the corresponding hydrogen gases evolve, but they don't react with the bases. However, only beryllium is the type 1 compound where beryllium reacts with the beryllium compound. So Be, it reacts with also NaOH. However, this reaction with NaOH makes it amphoteric in nature. Okay, so that is why it reacts to form the berylates. Berylates we discussed when we talked about the solubilization of barium hydroxide in excess of hydroxide. So at that time, I told that they form a compound called sodium berylate, which is nothing but Na2 BeO2 dot 2H2O plus what is released is the hydrogen gas. Okay, now what I would like you to do is I'll ask you in the class to balance this particular equation. Probably you require a water also here, because in aqueous solution this reaction is happening, so you require a water here. So balance this equation. So I'll ask you the balanced chemical equation for this reaction. So here beryllium is able to react with NaOH, and that's why we say that beryllium compounds are amphoteric in nature. Now here again, here again what we find is that we are talking now about the beryllium hydroxide being amphoteric, and this part I have discussed when we talked about the hydroxides of group 2 elements. So at that time I told you beryllium hydroxides are also amphoteric in nature because they react with bases to form the beryllium. Similarly, you will have the hydroxide also behaving as a having an amphoteric nature because it reacts with base to form the corresponding aluminate. Now, another anomalous property that the beryllium have is that they are rendered passive by treatment with concentrated nitric acid. Now, why they are rendered passive? When I say rendered passive, what do you mean by that? That they are made unreactive. Usually, elements group 1, even if it is group 1 or group 2, when they react with acid, they will form the corresponding halides and then or the corresponding salts, and they liberate hydrogen. That is the usual reaction that any element of the group 1 or group 2, when they react with acid, they will form the salt and release the hydrogen gas. But here, when you react it with concentrated nitric acid, beryllium, rather than forming beryllium nitrate and hydrogen gas evolved, this reaction is kind of rendered inactive. Now, why they are rendered inactive is because these concentrated nitric acid, they are kind of, if you remember somewhere, if you had learned about their property, they are actually oxidizing in nature. They are oxidizing in nature. So because of their oxidizing property of these concentrated nitric acid, what happens is that beryllium is kind of oxidized on the surface to beryllium oxide. Okay, so when this oxide layer forms on the outer coating of the beryllium, what happens? The further reaction with beryllium is kind of stopped. Okay, so that is why when you reacted with concentrated nitric acid, beryllium is rendered inactive or rendered passive. And the same situation you will also find in aluminium element. Now, coming to the beryllium, about the reduction potential values, the beryllium and aluminium have similar electron potential values. However, when beryllium is compared with other elements in the group, all the other elements in the group too, they will have a E0 value, which is approximately more than 2 volt. Okay, so that is why I'm saying that why these beryllium and the aluminium is showing similar reactivity can be said in terms of E0 value, because they exhibit similar kind of reduction potential values. Now, another anomalous property is that the beryllium salts are kind of hydrolyzed. Okay, now why do I say they get hydrolyzed? That is because one important thing that you have to remember is that beryllium salts that you find, be it beryllium halides or any kind of beryllium salt, they are usually not present. Like if we talk about halides, they are not just simply beryllium halides. They usually are present as their hydrates. That is, beryllium is usually present as in their hydrated form. That means you will find a hydrated complex of beryllium 2 plus, reacting with the X minus to form the corresponding halides. Okay. Now, so usually all the salt will be having this complex ion present in the beryllium. So whenever you take a solution of beryllium salt in water, what happens is that the beryllium salts undergo hydrolysis to form one of the product that is formed is the H2O 3 plus OH minus, that H is released and the complex now gets a charge of positive. Now what is released is a H plus ion which react with H2O to form H3O positive. Okay, so this is hydrolysis. The hydrolysis means breaking down of the water. So here one water molecule is kind of broken, that one of the OH bond is broken and H plus is released, and that's why the solution of beryllium salts are usually acidic in nature because they hydrolyze in aqueous solution. Now why this hydrolyzation is so easy is because the bonding that is formed between the beryllium and the oxygen is so strong that it renders the OH bond relatively weak. So that is why H plus is so easily released or hydrolyzed for making this aqueous solution slightly acidic. So reaction doesn't stop here, but rather many polymeric complexes are hydrolyzed complexes are formed in here. Okay, so that is why I am saying this statement that this beryllium salts are kind of hydrolyzed. That hydrolysis is possible because all the beryllium salts, since most of the salts are formed there from their aqueous solution. So all the salts, whatever the salt be, is always having a kind of hydrated beryllium complex. Okay, so that is why they undergo ready hydrolysis, and the solutions of beryllium salts are usually acidic in nature. Another important thing that you have to remember is the beryllium salts are mostly soluble. Now, solubilization can be easily understood because of its small size and high charge density. They are able to form these aqua complexes, and these aqua complexes is what the formation of these aqua complexes make the salts of beryllium highly soluble. So these aqua complexes is what make the beryllium salts very highly soluble. Apart from that, another thing that is important to note is that in group 1 only lithium formed carbide. However, beryllium compounds also form the carbides. But here, instead of the usual carbide, what is formed is this kind of carbon, that is Be2C, because what you expect is that when a group 2 metal reacts with carbon, it should form this kind of a carbide, that is Mc2. That is what you expect, right? But what is formed here is something, this one, that is BeC2. So beryllium unusually formed. Now other elements easily form, like magnesium, calcium, strontium, barium, they all form this kind of usual carbide. Okay, but beryllium, they form this type of carbide, and this carbide is called have a name of methanide. Now these methane, why they are called as methanide is because when these react with water, or when they are hydrolyzed in water, they release methane gas. Okay, and this is one important ways to get methane. So beryllium, from beryllium carbide you can get methane by hydrolysis. So that is why beryllium carbides are also called by the name of methanide. And another important carbide that is very useful is the calcium carbide, which is having the usual formula. Now this is called as acetylide. Now tell me why this is called acetylide. So that particular question I'll be asking you when we are going to discuss this in the live session. So please complete the equation. When beryllium reacts with H2O, they form methane. Apart from that, since it's reacting with H2O, it will form the corresponding hydroxide. So balance the chemical equation, and I will ask you the balanced chemical equation in this particular case. So I hope I made my points pretty clear. And if any doubts you have, you please ask me. Now, in the carbide, unusual carbide is also formed in the case of aluminum. So here I have discussed not only the diagonal relationship with aluminum, but also I have tried to explain you various different properties which are different from the other elements in the same group. So make sure you understand this, and in the live session we will also discuss about the structure of the beryllium hydride as well as the beryllium chloride. So thank you very much for your attention. God bless.